in lab this week, we're going to be taking a look at the shape and the connectivity of atoms when they form bonds in molecules, a topic in chemistry known as molecular modeling. While we are not going to be working with chemicals this week, we still got to demonstrate our knowledge of lab safety since we're going to be working in the chemistry lab room. So you're going to need to make sure you're wearing your scrubs the full time that you're in lab and wearing shoes that appropriately cover your feet completely with shoe material. We are going to, of course, apply our knowledge of covalent bonding. So we're going to be looking at the number of valence electrons that individual atoms have, how those atoms come together and form bonds. We're going to look at whether or not the electrons that are involved in that bonding is going to form bonding pairs or non-bonding pairs of electrons. We're going to figure out how many bonds are formed, of course, calculate some formal charges to make sure we've got the right connectivity that's going to result in the lowest energy structure. We are going to build some molecular models using the lab kits that are available in the lab rooms. And then you're going to practice drawing Lewis structures and drawing models on your paper using three-dimensional techniques, using those wedges and dashes that you were talking about in lecture class. When we talk about covalent bonds, we're talking about what forms when two atoms, typically nonmetals, share electrons between themselves. That's going to give them some added stability, and that is what forms a molecule. So let's talk a little bit about terminology when we talk about covalent bonding. We have first what are called bonding pairs. Those are the pairs of electrons that are shared between two different atoms. So if we go back to that example of water that we saw on the other slide, we see that there are two electrons that are in between the H and the O, the hydrogen and the oxygen, and those electrons are being shared between those two different atoms. So it's those two electrons right there. Those are bonding pairs of electrons. Now you can also see that there's two other sets of electrons that are not shared between the two atoms. They're sticking off to the side there of that oxygen. Those are known as lone pairs of electrons. You may also hear them called non-bonding pairs. And just as a quick reminder, again, in terms of terminology, a lot of the times you're not going to see molecules drawn out in the way I've got it shown there. Instead, you're going to see them with these lines between the two different atoms. These lines, they indicate a chemical bond. Okay, a bond between two different atoms. So hopefully the next question that's in the back of your mind is, how do we figure out how atoms are arranged in space, and how do we draw their structure? How do we know what they look like? Well, what we do is we use what's called Lewis structures, which talks about how atoms are bonded together in three-dimensional space, and it comes with, of course, because it's chemistry, a list of rules that we kind of sort of follow most of the time. The first of which is, of course, you try to figure out how atoms are arranged in space, forming kind of what we refer to as a skeletal structure. So it's just a basic first guess of how atoms are going to be arranged. And a lot of the time that's because we make these guesses on the spatial arrangement, kind of knowing already how atoms typically bond together. The next thing you want to do is figure out the total number of valence electrons. You're going to do that by, of course, adding up the number. And of course, if there's any kind of polyatomic atom or there's any kind of charge, that you've got to account for those in your total number of valence electrons. After that, you're just going to again start connecting your atoms together. You're going to start off with using up 2 electrons at a time, forming one covalent bond. And then as you work through that total number of valence electrons, once you've got a single bond between each one of the atoms, you go back and you look at those atoms and figure out which one of them, typically has 2 bonds, which ones typically have single bonds, double bonds, triple bonds, and arrange the remaining electrons around those atoms such that the octet rule is followed. All right, so when I kind of alluded to that we already know how some elements bond, we know typically that things like carbon loves to have 4 bonds. So you're going to see that very, very frequently. Carbon, of course, will also form double bonds. Then it will occasionally form a triple bond. So we've got to kind of keep that bonding formation in the back of our mind. Nitrogen, of course, has 1 lone pair, 5 valence electrons around it, so it a lot of the time likes to form 3 bonds. It, of course, will also form a double bond. not as much, not as frequently forming a triple bond, but it's not, again, beyond all realm of possibility. If we look at oxygen, oxygen with 6 valence electrons loves forming 2 bonds, and it loves keeping that lone pair. So we'll see it a lot of the times with 2 single bonds, or we'll see it a lot of the times with a double bond and 2 lone pairs. It will form a triple bond, but again, it's not that frequent. Sulfur, if we look back at our periodic table, sulfur is right underneath oxygen, so it's going to form a lot of bonds, a lot in the same manner that we see with oxygen. So you're going to see a lot of sulfur single bonds, and you're going to see some sulfur double bonds where you've got those 2 lone pairs. Again, one thing to keep in mind, hydrogen. Hydrogen has that 1 lone valence electron, so hydrogen is not going to want to form much more than a single bond. Halogens, things like fluorine. Remember, fluorine's got 7 valence electrons, so it's got 1 electron left that's not paired, so it's not going to be very likely to form any kind of multiple bonds. So you're typically only going to see 1 bond off of hydrogen and 1 bond off of any kind of halogen. I want to first start off saying, before I work an example for you, is that these steps, you can go through them kind of in any order. I typically start off with figuring out the total number of valence electrons and then guessing about what their relative orientation is in shape. Don't feel that you need to be stuck with doing these steps all in the same order. We do, as chemists, go back and forth in which step we do first. All right, so I'm going to work a quick example for you that of trying to draw out the Lewis structure for formaldehyde. Formaldehyde, it's got 3 atoms, a hydrogen, or 2 hydrogens, an oxygen, and a carbon atom. So we just got to take a guess about how they're connected together in space. I'm just going to take one guess and just say they're connected kind of like this. So now I need to figure out the total number of valence electrons. So we know oxygen, it has 6 valence electrons. Carbon, it has 4. Hydrogen, we have 2 of them. And hydrogen, of course, has 1 valence electron each. So that gives us a sum total of 12 valence electrons to work with. So we just added up, of course, all of the atoms, valence electrons over all the different atoms. If there was a charge, this is the point in which we would need to subtract or add electrons depending upon that charge. So we're going to start off when we got 12 electrons to work with. All right, so we're going to have our formaldehyde. I kind of was guessing around with the connectivity, and I'm just going to guess this is kind of our rough orientation of where the atoms are in space. So the next thing we want to do is start kind of connecting these atoms together, forming single bonds. We said on that other page that we have a total number of 12 valence electrons to work with. And in order to make a single bond between each one of these atoms, we've used up 2, 4, 6 valence electrons so far, giving us 6 valence electrons left. Okay, so we've got our connectivity kind of pieced together, and we've used up 6 of our 12 valence electrons total. I'm going to go ahead and show that. So we've got 6 valence electrons left. If we think about common ways that atoms bond together, we got to remember that hydrogen only forms single bonds. So we know that we don't want to form any additional bonds between the carbon and the hydrogen because our hydrogen, it already has its filled duet. It doesn't form an octet, it forms a duet of 2 electrons. So the hydrogen is really happy. So we got to figure out what are we going to do with our remaining 6 electrons. And the first thing we want to do is figure out if we can go ahead and start completing Adam's octet. We see that our carbon, it has already around it 2, 4, 6 atoms already around it. So really what we need to do next is try to form a double bond that would make 8 electrons around the carbon, giving it an octet. Okay, so we've gone ahead and given our central atom there a double bond. So it would fill up its octet. That means of our 12, we've already used up 6. We've used up another 2, leaving us with 4 valence electrons left to place around our molecule. And again, if we think back a little bit about how atoms commonly bond together and those common bond formations, I just showed a few slides back. We think about it a bit, we probably also have 2 lone pairs around that oxygen. Because otherwise, every other atom already has an octet except for the oxygen atom. It only had just 4 around it. It needed 4 more to make an octet. We had 4 electrons left, so that kind of makes sense for it to go in there. So like I said, a lot of the times, you may find yourself going through all the steps, doing them in a different order, doing them at a different pace to kind of balance out getting an octet all around all the different atoms. So, in our last step, like I said, we're going back, we're making sure that all of our atoms have an octet, who need an octet. Making sure we place valence electrons around atoms that would need valence electrons to satisfy its octet. And in the case of formaldehyde, we did have to go ahead and put a double bond between the carbon and the oxygen atoms to satisfy the octet of both the carbon atom and the oxygen atom. There are, of course, exceptions to the octet rule that you just kind of need to keep an eye out for. The first of which is an incomplete octet. We kind of already ran into one of them in the fact that, hydrogen only needs to have 2 electrons in order to form a duet. That will give it its equivalent to an octet. You have, of course, the atoms over in group 2 and group 3. So like beryllium, Be, it's got 2 valence electrons. It really needs those 2 electrons paired before it's going to be satisfied in a more stable conformation. You also got boron, and those in the group 3 column with 3 valence electrons. Once they've paired off those 3 electrons, they really do not want to form any more bonds. So that's one of the things that you're going to commonly see. A really common example, of course, is BeF3, boron trifluoride. Again, using boron with its 3 valence electrons. So we can just go ahead and add those valence electrons. Bonding to fluorine. Remember, fluorine is a halogen. So it's only going to want to form 1 bond as well. So it's going to form 1 bond with that boron. It'll form, we got 2 more of them, both of which are going to form just, of course, a single bond between the boron and the fluorine. Another thing occasionally, and about the only one that you're going to come into contact with in terms of the odd electron rule, is that of NO, nitrous oxide. Nitrogen, of course, has 5 valence electrons. Oxygen has 6, which totals 11 valence electrons. At 11, that's an odd number. So right there, it should be your sign that you're going to have an odd electron exception, the octet rule. This is, of course... This ends up forming what looks kind of like a really weird structure where you have a double bond between the nitrogen and the oxygen atoms, and that single electron, odd electron, kind of alternates in between the nitrogen atom and the oxygen atom in what's known as a resonance structure. The last exception you'll probably typically see with the octet rule is that of the expanded octet. This occurs with atoms that are on the 3rd and 4th and farther down on the periodic table who now have d orbitals. If you remember those d orbitals, that's when you start seeing more than 8 electrons in a particular orbital subshell. That, of course, is going to result in there being more than 8 electrons around a particular atom. One of the examples, that you'll see in general chemistry is that of PBr5, where you have phosphorus, which has 5 valence electrons. Bromine, of course, has 7, and there are 5 of those, giving you 35 valence electrons for a total of 40 valence electrons. Phosphorus, it turns out, will be at the center, of course, because, bromine is one of those halogens, which typically is only going to want to form 1 bond. So the phosphorus is going to be in the middle, surrounded by bromines. 3, 4, and 5 of them. You're going to, of course, connect these together, all with single bonds initially. Make sure that your bromine, everything else, all has 8 valence electrons around them. So it has the octet. If you go through and count real fast, 8 times 5, because there's 5 bromine atoms. Each one of those bromine atoms should have 8 electrons. That's 40 electrons used, so we have none left. But if you look at that phosphorus atom, it has 2, 4, 6, 8, 10 electrons around it. So it's an exception to the octet rule by forming that expanded octet. What you probably notice when I'm drawing Lewis structures is that I go ahead and kind of give a shape to the arrangements of atoms in space, and that's following the Vesper model. That's valence shell electron pair repulsion theory, which visualizes electrons as wanting to, they're of course negative charge, and so any kind of negative charges, if they get near one another, they're going to repel. So it's kind of visualizing electrons as wanting to take up as much room and be as far away from one another as is possible. So that's going to cause those atoms to move out of linearity with one another and causing things to kind of contort and bend a little bit. And that's, again, it's all about those electrons repelling one another. So the next 2 slides kind of summarize really the Vesper model and the shapes that are possible with using the Vesper model. And we look at them in terms of how many electron groups or electron pairs there are around that central atom. And then how many, and how they're bonded together, whether that's through bonding pairs or lone pairs. And depending upon whether it's a bonding pair or a lone pair, that's going to cause a difference in the shape of our structure. So again, this is looking at, again, it's summarizing that Vesper model, looking at the number of electron pairs and how, depending upon whether or not those electron pairs are bonding pairs or non-bonding pairs, you're going to have a distortion in the shape. So as you get more and more electron pairs, the shapes, there's more possibility of the type of shape, and you're going to see some more distortion. For instance, if you got 5 electron pairs surrounding your central atom, you could have a tetrahedral where everything is surrounded by a atom. You can have the sawhorse. You could have a T-shaped, or you can have a linear structure, again, depending upon the number of bonding pairs or the number of lone pairs. So you really got to pay attention when you're drawing those Lewis structures and make sure you can identify how many bonding pairs and how many lone pairs there are in each one of those structures. And you do need to make sure you memorize the vast majority of these shapes. If you need any kind of help when you're working through your assignment, please make sure you jump on and talk to this TA in the Learning Center. Send your TA a email or send me an email.